Hello everyone, and welcome to the Force of Gravity pre-lab. Today what we're going to do is a lab on the force of gravity. We're going to investigate it a little further and more completely, because after all, it's a force that we've put on pretty much every system, schema, and force diagram we've drawn. So, compare, if you will, the force of gravity acting on the female soccer player and the football player over here. Will those forces of gravity be the same? I mean, if we put them on a bathroom scale, would it read the same for both of them? Well, of course not. Right? It's a much bigger guy, right? So what's different about him? What's fundamentally different that makes his force of gravity more than the force of gravity of the soccer player? Well, my supposition would be that he has a lot more mass. So, in this lab, we are going to create graphical and mathematical representations of the relationship between the force of gravity and the mass of an object near the surface of the Earth. And so we're going to see here, is there a relationship between how much mass something has, which remember is the amount of matter in an object, the protons and electrons and nuclei and neutrons and all that stuff, and how much the Earth pulls on it. Now, if we're going to do a quick little force diagram here to see what's going on, we're basically going to hang these masses from a spring scale, and you'll see that in class. And so if we do a quick system schema, we have the masses, definitely interacting with the Earth through a force of gravity. And then the masses are also hanging from the spring scale. And so there's a force there. Now, I'm going to be a little more specific about this force, not just applied. It's going to be the force exerted by the spring, or the spring scale. So there are two interactions going on, and there are two forces. There's no normal force here because it's not sitting on a counter or a surface, and it's hanging from the spring scale. So if we do a quick force diagram, force of gravity, of course, acts down. The spring scale, of course, acts up. It is moving at a constant velocity, or actually it's not moving at all, and therefore those two forces are the same. So, if we read the force that's being exerted by the spring scale off of the spring scale, we'll then know the force of gravity that are acting on those masses. So that's basically the lab. We're going to change how much mass we hang on the end of the spring. And so the mass will be our independent variable, the one we control, and then we will measure the resulting force of gravity. So when we get to a graph eventually on LoggerPro, force of gravity on the vertical axis, mass on the horizontal axis. Now, one thing that we haven't talked about is that we haven't really put numbers to forces in this unit. I mean, yeah, we've drawn a lot of diagrams, we've related them one to the other, but we haven't really said, what are we going to measure forces in? Well, in the English system that we use here in the U.S., and pretty much only in the U.S., we measure forces in what you would read on a typical scale, pounds. But that's not the force units that are used in the international system of units. Those are named after our old friend Isaac Newton. So the Newton, capital N, is the SI unit of force. It's a capital N because it's named after a person. You know, there was an Isaac Newton. Now, how big is a Newton? Well, it's going to take us a couple of units before I can really completely define why a Newton is the size it is. But suffice it to say that 1 Newton is about 0.2248 pounds. Little less than a quarter of a pound for every Newton. Or flip it around, right? 1 pound is about 4.448 newtons. So 1 pound is a little less than 4.5 newtons. Okay, this is the one that I normally think about here. 1 newton is just a little less than a quarter of a pound. So it's a smaller unit of force than the pound is. Now, of course, we're going to have to keep a nice data table here. And so we have mass in kilograms. And you can read the masses right off of the masses themselves. And then the force of gravity in newtons, which you can read off of the spring scale. I would like you to do 50-gram increments, all the way from 50 all the way up to 1 kilogram. That might seem like a lot of forces, but it doesn't really take that long to measure all of them. Now, a couple of things. There are 2 different kinds of spring scales. Okay, one spring scale, the brown one, only goes up to 5 newtons. The green one goes up to a full 10 newtons. So you're going to start with the brown one because it's going to be a little bit more precise. And then when the force gets too big, move over to the green one. Okay? A couple other things. The mass hanger, the brass mass hanger that we're using, has a mass itself of 50 grams or 0.050 kilograms. So notice that the first reading you're going to do is just hanging the mass hanger on the spring scale. Right? Just the mass hanger, and then you're going to add 50 each time. One other little thing here. This is a scale, and so if you want to make sure that you use it to its full precision, you need to estimate, estimate, estimate. Right? Don't just round off to the nearest hash mark. Estimate in between, right? Like we talked about in Unit 0. So good luck, and when you're done with this Force of Gravity lab and you've graphed it, call me over so I can look at it, and then you will be entering the slope of this graph into a Google form on the website. Thank you very much.